Hello everyone, my name is Sharath and today I'll be talking about our paper MapVerse, a benchmark for geospatial question answering on diverse real-world maps. So first let me begin with the understanding of why map understanding matters. Maps encode dense real-world knowledge that's integral to everyday life. It has a wide variety of applications like navigation, climate, demographics, etc. It requires spatial, visual, and symbolic reasoning and hence can be pretty diverse, complex, and challenging. The problem with existing benchmarks is that they have a limited domain coverage. For example, most of the previous papers focused on choropleth maps. They lack real world maps, as most of them are generated synthetically. The question answers are also generated synthetically using templates by leveraging VLMs. As a result, you don't find human-generated question answers. There is lack of diversity in map categories, question types, as well as answer types. As a result, it also has lack of in-depth analysis. The contributions of our paper is that we work on real-world maps with question answers generated by humans. We cover a diverse set of categories and provide fine-grained taxonomy to help us evaluate it better. So now let me talk about our data collection process. So first we collected different sets of maps from the web and then did some quality filtering to weed out blur, low resolution, or too complicated and irrelevant maps. Then we had our human annotators who would provide question answer pairs to each of these maps and which were verified later before doing the metadata labeling for each of these question answer pairs along with the maps. So the key features of our dataset is that we have close to 1,025 real-world maps, along with 11,837 human-authored question-answer pairs. There are close to 10 map categories, 8 question reasoning classes, 6 answer formats, and 12 geographical granularities. We have benchmarked our results on 8 open source and 2 closed source VLMs. So just to give you a brief overview of our data, we have 3 sets of disjoint classes for visual reasoning, spatial reasoning, and comparative reasoning. So these are the set of answer types on the right that we have used. And the set of map categories and its distribution can be seen below, ranging from network to cartogram. To give you some examples, on the left, we have a cartogram map with Boolean, counting, and ranking type questions. And on the right, you have multiple sets of maps, which requires question answering based out of comparison and some numerical calculation. So the experimental setup was as follows. The inputs were given as an image plus text format, where map is the image and the question is the text, and expected answers as a text from the VLMs. So we did two types of settings, one with image plus text and second with text only to see how much muscle memory is being used. The metrics that were used for each of the answer formats is as follows. So the prompting strategy that we used was a single standardized instruction prompt with few short examples. The evaluation results were as follows. So the best performing open source model was Qwen 2.5 VL, and the best performing closed source model was Gemini 2.5. So to give you a metadata-wise analysis, we saw that the marker maps were easiest for the VLMs, and unexpectedly, the choropleth maps were relatively harder. The performance was very good on global level or world maps compared to other geographical granularities. The performance was better on visual than spatial, which in turn was better than comparative. To conclude, we introduced a MapVerse dataset that benchmarks for geospatial reasoning in VLMs. The low accuracy across different answer formats indicates that geospatial reasoning still remains challenging. So the limitations of our work were that we leveraged manual prompts and fixed set of few short examples that ended up limiting our scalability. The future directions in which we can expand upon are that we can add more map categories and reasoning tasks. We can also include temporal dynamics, improve prompting strategies, and try fine-tuning models on MapVerse dataset. Another thing that we can add is we can design specific architectures for geospatial reasoning. Thank you.